Thank you, Chris. And I want to give a special thanks for our advisory board from the center and all the work they've been doing for us over the last couple of years. Peter, it's good to see you again. It's my pleasure to be able to speak today and to talk about climate change. I spent my life on this, and I think that tell you a little bit about our ice core research program here at Byrd Polar and Climate Research Center, and particularly the records coming from the highest mountains on this planet. I want to start by saying that we are a team, and we have an outstanding team. This is our current team here at Ohio State, but for the past 40 years, we've had outstanding people here at the center. We have bridged to other departments, the Department of Microbiology, and we share a postdoc, Chapang, who's here in the audience. We're doing some research that could not be done just by glaciologists and climate scientists. So we can bridge these gaps. We also have a group of scholars nationally and internationally, and our program would not be possible without the collaboration of all of these people. So I want to start by the beginning of this program, and this is very much an Ohio State University program. Back in the mid-70s, when I came here as a graduate student, all the research on ice core research was done in the polar regions. And it was during doing my PhD comparing climate records from the first core drilled through Greenland with Antarctica, excuse me, that's supposed to, yeah. I realized we needed something in between. And when we first took aerial photos to the program manager of polar programs, he thought this could be important, but he said, you know, my mandate is only to fund north of the Arctic Circle and south of the Antarctic Circle. But in 1974, he scrounged up $7,000 and asked, what could you do on that tropical glacier for $7,000? And we said we thought we could get there. So our first trip into the tropics was in 1974 to the Quelccaya ice cap. This ice cap sits above the Amazon basin. It approaches 19,000 feet in height. And in the mid-70s, it was a 2-day journey by horse from the end of the nearest road. So the challenges of how are you possibly going to drill this ice field? It took about a decade to figure out how to do that. But in 1983, we used the very first solar-powered, lightweight drilling system, what was designed for this project, to recover not one, but 2 cores, 550 feet in length, and to bring back, at that time we didn't have the technology to keep the ice frozen, we brought back 6,000 bottled water samples. And from there, we produced the first tropical history from a glacier in the Andes of Peru. Now, I have to say, I've been working on ice cores for over 40 years, and they are amazing. They record not just climate, things like temperature through the isotopic composition of the water that makes up that ice, but also precipitation, where you have annual layers, but they record the forcings of climate, the things that cause our climate to change. Volcanic eruptions, tephra, sulfate layers. We have a history of the output of the sun through the cosmogenic nuclides that are archived in that ice. And they also record a very important thing that we're concerned about today. It's our only real capsules of the atmosphere from the past. And we now have records from Antarctica that go back 800,000 years that allow us to look at carbon dioxide, methane, nitrous oxide, all of those things that we're really concerned about in today's world. But everything has a history. And back in 1988, the National Science Foundation had their first call for science and technology centers. Ellen and I applied for this, and this was the map that we showed of what we wanted to do. It got good reviews, but it didn't get funded. We asked for $9.5 million to do this. So 33 years later, one NSF funded program at a time, these are the cores that our team has been able to recover. We forget often that we live on a sphere. And because we do live on a sphere, over 50% of the surface area of this planet is in the tropics, between 30 north and 30 south. Over 50% of the 7.8 billion people on this planet live in this zone. So it's very important to understand both natural and human-driven climate change. It takes a special team of people. We work in extreme, high elevation environments. This project couldn't be done without those people. And this is a view in 2019 of our team going up Huascarán in the Andes in Peru. We have had over 400 scientists, postdocs, students on these projects, in addition to over 500 porters, Sherpas, mountaineers that have made this possible. I mentioned the fact that we had an issue of how do you keep ice cores frozen? We've had the opportunity to drill in 16 countries, in addition to Antarctica and Greenland. Every country is different with the logistics. But to give you an example, this is in the Himalayas. In the Himalayas, we can use Sherpas to move ice from the drill sites down to the edge of the glacier. But when you get to the edge of the glacier, you're still 400 feet from the plateau where you can bring in freezer trucks. So we have to use local transportation. If you're in the Himalayas, those are yaks. And these are insulated boxes. There's 6 meters of core in each box, 12 meters for a yak. We drill 500 to 600 meters. You have to have a whole herd of yaks to get the ice to those freezer trucks. Then there's a dash to Lhasa, and then it's air cargo back to Ohio State. Once we get it in the freezers, then we have to have the labs to do the analysis. And we're very fortunate to have a class 100 clean room in which we measure dust and major ions, black carbon, trace elements, and more recently microbes. And we have an isotope lab just down the hall here for measuring stable isotopes. We have storage facilities for those cores out back, very important. And we also have a machine shop in which we design and build our drills for these programs. So a lot of people, a lot of different disciplines make this possible. But these cores allow us to look at the past, and I'm going to say just a few words. You can see the margins of the Galia ice cap in far western Tibet and Kelkaya. And each of those annual layers come in areas where we have a very distinct wet and dry season. And when you drill the cores, often you can actually date the cores annually by counting those dust layers. So they're a perfect, beautiful archive of our past. We measure many things. I'm not going to bore you with all of those, but here's two. If you look at isotopes, this is a 5-meter section of the Kelkaya ice core. Every annual cycle is preserved. This is a period from 1800 to about 1830. Every dry season, there's a dust layer. Measure the thickness between those dust layers, and you have a precipitation history from the past. The other thing remarkable about these cores is their reproducibility. Here's the very first record from Kelkaya, based on those 6,000 bottled water samples. Last 1,000 years, 10-year averages. And 20 years later, when we obtained the ability to bring out frozen ice cores, here is the same record from that ice field. And when you look at that, you can see that from 1,000 to about 1,500, it was warmer than average. We go into the little ice age, which was cooler in the tropics. And when we come into the 20th century, it's warmer than normal. Take those annual layers and look at the precipitation history, and you can see the brown areas are less than normal. The blue areas are above normal. And so there's a history of precipitation. Now, one of the beauties of working in the low latitudes, that's where civilization as we know it has developed. And in the Andes of Peru, there's a long history before the arrival of the Spanish. And we can take that precipitation record that we have from Kelkaya that goes back to 200 AD and work with anthropologists and archaeologists and look at how climate impacted those societies. And when you look at this figure, you'll see that in the early part of the record, when it was dry in the highlands, all the cultures were on the coast and the capitals were on the coast. When it became wet in the highlands, people moved to the highlands and the capitals moved to the highlands. When it became dry again, those highland cultures disappeared and we had the development of the coastal cultures. And then on the onset of this very wet period, we had the rise of the Inca Empire, which was the largest in South American history. And it came to an abrupt end with the arrival of the Spanish in 1531, which we can use this ice core to actually contribute to many, many different disciplines. In the 1980s and 90s, this was the advent of this tropical ice core recovery. We weren't talking about climate change or global warming. We were looking to reconstruct the history of climate in these remote parts of the world. So in the Andes from Calcaya, we had the first evidence of the low ice age. From Huascaran, we got the first records of the last ice age 20,000 years ago when Columbus was under a mile of ice. And from the Himalayas, we got a history of monsoons and monsoon failures in the past. So they're wonderful archives. These were published in a lot of science and nature papers at the time, but it was in the collection of a global compilation of records we started to become concerned. And if you look at the isotope indicator of temperature from a combination of all of these records, you can see for the last 2,000 years how unusual the last 50 years have been. And if you look at IPCC report that came out last month, here's a compilation of all the paleo records we have on Earth for the last 2,000 years. And the warming is unprecedented in more than 2,000 years, according to all of our best recorders of our past. This brought me in 1992 for the first time to join a number of climatologists who testified before the US Senate on the climate change issues and our concerns. And the ice is a wonderful recorder of the past, but it also is an indicator of change. So here's a couple pictures from the Calcaya ice cap. This is Coriolanus Glacier. I see Henry here spent a large part of his life actually mapping this glacier. This is what it looked like in 1978. 40 years later, this is what it looked like. A lake now covers 84 acres. It's over 200 feet deep. On the right is that margin layer, the Calcaya ice cap. 1978, 24 years later, this is what it looks like. And it brings home the message. We're losing the history that's in the ice, but we're also losing a very valuable water resource for the people who live downstream from these ice fields. Takes you to one other site. Most people don't realize there's a glacier in Papua, Indonesia, and New Guinea. But in the middle of the tropical rainforest, there is. And in 2010, our team drilled these two domes of this ice field. Here's the same place just earlier this year. And you can see how rapidly the ice is disappearing. And back in 1992, from this Landsat image, you can see the ice in blue. By 2009, this is what it looked like. And by 2020, it has practically disappeared. And in a couple of years, the only ice from this glacier will be archived in the freezers downstairs here at Ohio State University. But what we see happening in New Guinea and on Calcaya and on Kilimanjaro and north of the equator in the Himalayas is very much the same. And there's a Chinese philosopher over 2,000 years ago, Liu Zhu, who said, if you do not change the direction, you may end up where you are heading. And all of these glaciers are likely to disappear in the near future. And the impacts are not just telling us about what's happening to climate, they're directly impacting indigenous people who live in these areas. This is a view of the Calcaya ice cap in July of 2005. This is a family that we interviewed in 2018, husband, wife, son. They raised 400 alpaca in the valleys below. This field, there's often when we're mapping, there's alpaca there. And this, you can see the field in July of 2006. It's covered with sediment. It's covered with sediment because an avalanche in March came off the ice cap, fell into the lake, created a mini tsunami, and drowned many of their alpaca downstream. And the point here is that this lake didn't exist until 1991. So these are new geohazards for the people who live in those areas. So I'll say a little bit about the future. Here's a quote from Ernest Shackleton back in 1915. What the ice gets, the ice keeps. And of course, he was talking about his ship, the Endurance, that led to this epic journey out of Antarctica for his men. But it's true for ice cores, and it's true for what the glaciers have captured. And on the Calcaya ice cap, Back in 2002, we discovered the very first wetland plant being exposed by the retreating margin of this ice cap. We were able to date that, and since 2002, we have collected a whole series of plants and dated them. And as the glacier gets smaller, the plants get older. The oldest plant we've collected in 2018 is over 7,000 years in age. These are wetland plants, no woody tissue. Had they ever been exposed in the last 2,000 years, they wouldn't be there. So they tell us what's happening on this ice cap is unusual over the last 7,000 years. And we see that in the ice core records that we have spent our life retrieving. These are cores that we've drilled from the Cordillera Blanca in northern Peru, starting in the 1990s. You can see how the records are washed out at the lower elevation. That's because melting is occurring. Firn is porous, the water moves through, erases the record. The only place that record was preserved in 1991, 1993, and we took a shallow core in 2016, was Huascarán. So that led us to write another proposal to the National Science Foundation to drill this, the highest tropical mountain on Earth, which we did in 2019, drilling 2 ice cores from the col between the North Peak and the South Peak, and drilling the highest ice cap, tropical ice cap on the planet. And this was in the summer of 2019, and these cores, which are in the freezer, have kept our lab running through the pandemic. And so it was a very good timing for that. And we drilled 2 cores in the col. They are 550 feet in length, each of them, and 2 from the summit that are over 215 feet in length. And they have a tremendous history. We're doing our normal measurements, but we're also doing new measurements. And this is the thing that has happened in my career. The things we can measure now, we couldn't measure 10 or 20 years ago. And this archive is very important for that. For example, we have a black carbon record that we're now producing, and Emily and Roxana, who are research scientists in our group, are working on that. And we hope to reconstruct the 20,000-year fire history of the Amazon. We know nothing about that long-term history. We're working with Japan and our colleagues over in the microbiology department to look at the history of microbes, bacteria, and viruses. And ice preserves everything that falls onto these glaciers. And this is just getting started, but we are in a very unusual position here at the Byrd Center. We have the most geographically diverse collection of ice cores on this planet down in the freezers here at the university. This is a view of South America, looking in the Amazon. And Austin Weber, who's in the audience, to check his poster and check Shiping's poster if you want specific information. But he's looking at deforestation, and we're trying to look at, can we see a record of deforestation preserved in the Huascarán ice cores? Because the air in the wet season moves across the Amazon into easterlies and up on the Andes. But we know very little about the long-term history here, but I have to show you this. One of the things we have when we look at methane on this planet, we only have records from the polar regions until Huascarán. Just last week, I got the very first data from Ed Brooks' lab out in Oregon State that measures methane in the polar cores. The green is the methane records from Greenland. The blacks and blue are from Antarctica. And these are our first results from methane measurements on those cores. I think we have and will have the very first tropical record of methane right above the largest methane producer, natural producer on Earth, the Amazon basin. So they hold a lot for the future. This is the view from the summit of Huascarán, looking to the west. At night, you can see the lights of the cities in the valley below. Water for those cities comes from the Rio Santa River. And if you go down to the north, there's a hydroelectric plant, Santa Cruz hydroelectric plant. The river goes around and comes back out to the coast. And through this gap, you can see lights from the city of Chimbote, 400,000 people. All these people depend on water in the Rio Santa River. And during the dry season and during periods of drought, that water comes from melting glaciers, and all those glaciers are becoming smaller. If we look into the future, this is a projection of how temperatures will change with height on our planet. going from 90 degrees north to 90 degrees south. This is RCP 8.5. And you see the Arctic amplification of temperature we hear a lot about, but there's also a low latitude application of temperature with elevation. And these are the elevations of where all of our cores exist. So if you have a 2 or 3 degree warming at surface, you're going to have a 5 to 6 degree warming at the elevation of these glaciers. That puts their water resources in the future at risk. And of course, those glaciers are melting. We know sea level is rising and it's accelerating. It's now rising at 3.4 millimeters per year. It has risen 8 inches over the last 100 years. And 25% of that rise is coming from melting of the mountain glaciers. The polar glaciers are starting to melt now, and they're going to play a bigger and bigger role as we go into the future. But it's interesting to ask the question, what if we lost 10% of the ice that's now, the volume of ice that's on land? What would our coastline look like? Here we are today, lose 10%, this is what it looks like. And unfortunately, over 50% of the world's largest cities are coastline cities, and they're subject to being impacted as we go forward in time. So let me conclude here by just showing our global collection of ice. We already know in all of these sites that melting is occurring, and we're losing that history from the past. I believe that will continue. Downstairs, we have over 4.5 miles of ice collected over the last 40 years. We have an archive preserved. Some of those ice cores come from glaciers that no longer exist in our national world or our natural world, and they should be preserved for the future. This is our vision of what that future would look like, doubling the size of that freezer and renovating the freezers that we have to ensure that that archive is there for the young scientists that are coming along. And so let me just end with a quote from Martin Luther King, and you can read this, I'm not going to read it, but I would say that for global climate change, nature is the timekeeper, and unfortunately none of us are wise enough to know how much time we have to make the necessary change in order to make this world sustainable for ourselves and for our children. And for most of the mountain glaciers, it's already too late, but I still think there's time for us if we act soon. So thank you very much for your attention.
Thanks, Lonnie. So we have time for questions. If there's any online questions, you can use the, like, hear me. So we have time for some questions. Those online can submit questions with the Q&A function. And otherwise, we can take questions from the audience.
Yeah, Lonnie, obviously, as you pointed out, Thompson is under a mile of ice several thousand years ago. And so you have two issues. You've got natural precision of glaciers, as a function of the length of cyclicity, and you also have precision of glaciers as a function of water. How do you separate out those two issues?
That's an excellent question, and it's something we
Just repeat so that folks online
can
hear. Yeah.
Yeah. No, the question is that glaciers have always advanced and retreated in the history of this planet, and how do you separate out natural forcing from human-driven forcing? And it's an excellent question, and we know that, for example, during the Little Ice Age, Earth was cooler due to less output of the sun and more volcanic eruptions, and glaciers advanced, and they've been retreating since the end of the Little Ice Age, about 1880. But what's really unusual and what makes, and if you go back further in time, Columbus, Ohio was under a mile of ice and sea level was 120 meters lower. But the difference today is that we have never had 7.8 billion people living on the planet, depending on all the resources. And the real change that has occurred in the last 50 years. It's not that the glaciers are still retreating, it's they're accelerating. And that is what links it back to greenhouse forcings that we're all concerned about. So, but it's it's a great question, and that's why you need those long perspectives. How did the system work in the past?
So you have direct evidence, that was what kind of, you have direct evidence of that rate of acceleration. During the past.
Yeah, and I mean, there's a whole lecture I could give on how we actually fingerprint what's forcing climate on this Earth. But over the last 100 years, you cannot explain the temperature rise in the last 50 years using natural forcing. The only way you can do that is to put in the greenhouse gases. Yeah, but it's a great question.
We have an online question?
Yeah, we do have an online question. So the question is, how is it going with communicating with policymakers about this, and how can we as the public be involved in helping urging policymakers to help mitigate climate change?
I think that's an excellent question, and it's something we have tried to deal with. Now, how do you change policy? And it's an issue at all levels. But what I learned in 1992, I was very optimistic at that time, testifying before the U.S. Senate. All of our funding agents were working together, and I thought we were going to make big progress toward moving toward sustainable energy. But as time progressed, this unfortunately became very much a political issue, and it kind of divided the country. Climate change is not political. It's about us and all human beings on the planet. And it's not just the U.S., it's all of us that are being impacted. And so how do you change? And I can tell you this. My daughter, 10 years ago, told me, said, "Dad, one more ice core, you're not going to change the world." She said, "You got to reach millions of people." So over the last year, I tried a TED Talk, and we have a documentary coming out called Canary. It's an hour and a half that'll tell the story of this research group, of what we've observed, but it's a personal story. And we're trying to, and it's to actually inspire the next generation of young scientists. And so, yeah, how do you change? How do you bring about change? But clearly you've got to reach millions of people to do that. Politicians are elected. If people speak out, they will change directions. And so this is something I think we all have to work on, and we all can contribute in different ways to make that happen.
Thank you, Lonnie.
Yeah.
All right, thank you very much, Lonnie. Well, as we switch over, I'll introduce our next speaker, Professor Bryan Mark, faculty in the Department of Geography. And he is the leader of our Glacier Environmental Change Group. And so his group links the ice to the people. I think that's how he puts it. So we have, as Lonnie showed in his talk, we have populations dependent on glaciers living in and around alpine environments. And Professor Mark's group explores those interactions using pretty much every tool there is, including drones, and right from drones to GPS to a shovel. So we will hear about his program momentarily. All right, so giving the next talk, Glaciers No More, Exploring Dimensions of Tropical Climate Change in the Andes. Take it away, Dr. Mark.
Thank you very much. You might want to reconsider after you hear what I say, but I thank you, Ian. Ian's a great leader, and he's my peer, but he's actually younger than me. And at this point in my career, my life, if I'm not stepping up to leadership, I guess I get the short straw to give the talk. But it's actually an honor to do this and to follow Lonnie, because I've literally followed him my entire career. And what I want to do, there's two nuances to this title. Glaciers No More is one way to think about looking at the environment where glaciers used to be, and trying to understand the climate dynamics that explain why they're not there now and how to understand our current situation in light of that. But also to think, of course, what's going on as we lose them, as they're accelerating in their recession. So I position myself below Huascarán that you see here on the right side of the screen. And when you start to look at where those glaciers come out into the valley floor, where people are making a livelihood, you see large moraines that you can see in the middle picture that indicate that these glaciers were much larger in the past. And arguably the remaining ice is just in the boundary condition of nothing at this point, compared to their large extents of the past. But of course, this continuity goes all the way to the coast. So what I want to do is kind of reflect on that 2 dimensions, but there's a third dimension that's emerged in the process of preparing this. Lonnie's quote by Martin Luther King was all about time. I too got forced into a TEDx talk by social obligations because the BFF of my daughter had a parent who was organizing the talks and I couldn't say no. My argument was about putting time in the denominator to look at the comparative rates of change. But right now, as I think about Glaciers No More, and I started to pull together this talk, I was procrastinated, like Martin Luther King talked about the stealing of time, because I'm a procrastinator. And it was really hard to pull this talk together. I've done this talk maybe many times, but I decided I was going to not do those same slides because we're in a difficult situation, and I may not be able to get to see this wonderful landscape in the same way that I have into the future. Because if you think about it, we have been incredibly privileged to do this science because of cheap energy. My group is full of young, inspiring graduate students. These are the current ones here, and I'm going to highlight the work that they're doing in this domain. But we call ourselves Glacier Environmental Change because we like to think about glacier changes over many different time scales, spatial scales, and how it's impacted the environment. And I've also recently started a collaborative group effort with other faculty in the Department of Geography, Shengyu Liu and Yungtao Bao, who are part of a project to think about integrating coupled atmospheric oceanic modeling into our glacial modeling. And so, but also, this is a fascination of ice as a liquid frozen reservoir that's obsessed the Byrd Polar and Climate Research Center for over 60 years. And I'm really part of a historical dimension. So what I want to do today is highlight not just what we're doing, but kind of who along the way. The tropical Andes are a fascination of mine because as a geographer and as kind of ADD, I see this geography as unparalleled as an exciting contrasts and gradients. And what you see in this oblique photo put together, it's a satellite image draped over a digital elevation model that my PhD student Forrest Chesso put together. And you can look towards the east and see the Amazon as this basin that Lonnie pointed out is this wonderfully humid and methane rich environment. But all the precipitation that falls to make the snow and ice to make the glaciers in the tropics comes from this direction. And you can see that this barrier of mountains that is the Andes, what this looks like. And you can also get an appreciation for some of the really relatively small areas that are glaciarized. But yet right here at the Cordillera Blanca, we have more tropical glaciers than any other place on the earth. And as Lonnie pointed out in those wonderful images from Huascarán, which is the highest point in the Cordillera Blanca, as those glaciers drain, they go to the west coast, which is a desert. And so this is important to remember because of coastal cities. And when we look at the historical perspective that Lonnie's able to give us through the ice cores, we know that civilizations have waxed and waned in this environment for millennia. But right now, Lima is the world's second largest desert city, and nearly 1.5 million Greater Lima residents lack running water. So they have to get this trucked in. But when you look at the globe, Peru itself has 4% of Earth's freshwater as a result of being right there at the heart of the tropics. And a lot of exciting cycling of that water, but only 2% of those water resources are available on that arid coast. So we have to think about glaciers over different timescales. And so I'm going to take you to a couple areas in the Cordillera Blanca here. This is the Geschke Valley. And if you look on the left panel, you look up and see what the modern glaciers look like. They're thin and they're accelerating in the recession. And this photo was actually taken in 1998. And you can see the little ice age moraines draped there. indicating where that ice was larger in the recent past. But if you turn around and look backwards, you can see much larger moraines and lakes in the landscape. These are really old. How old? And how big was that ice? And how quickly did it change and why? Are some of the questions we can start to get at when we look at these landscapes below the modern ice. This is all the domain of glacial geology. And the simple questions are kind of what patterns from late glacial moraines and lakes can we see in this landscape, and what do they reveal about the forcing climatically of this recession? And so how do we get at this? What you see here in this photo are some of the rare, amazing species. As a reminder that this area is a biodiversity hotspot as well, being right there at the core of the tropics. And these Puya Raimondi bloom once in their lifetime of 70 years. But there they are, perched on a lake glacial moraine. You look down at the lake, you can see the bounding moraines that make that lake. And the coring that we do to get at the sediments gives us a view as to what's been going on since that moraine was in place, i.e. when that glacier was sitting in the landscape at that position. But in this, I have to give tribute to John Mercer, who's one of our important members from the Byrd Polar Climate Research Center. Of course, he at that time was part of the Institute of Polar Studies. And he had a vision that was quite large, and I'm going to come back to his vision towards the end of this talk, but he was fascinated with the growth and decay of ice sheets over the globe and had some really important insights to make. And he realized, of course, that the tropical glaciers are really small relative to the ice sheets at Antarctica and Greenland. But he realized that they're really important to understand the relative timing of their changes, because that will give us some clues as to how the climate on this global system works between hemispheres. He ended up being the guy who's really active and fit. And I never got the chance to meet him because unfortunately he died relatively young, 65, I think. I can't quite do the math that fast, but you could. And he used to be able to get across this landscape in a way that just blew my mind, because I tried to follow where he went as a graduate student and try to recover more datable material in the landscape, radiocarbon dating material, to figure out how old this landscape is. But when I started my graduate career, he was the only guy who had a maximum limiting age. So he was able to find carbon buried by till that indicated the ice had advanced over it. So that gives us a maximum age of that moraine. I also follow in the footsteps of two really prominent, in my mind, Byrd Fellows. And one of the wonderful things that we do here at the center is we sponsor postdoctoral fellows. Jeff Seltzer and Don Rodbell were fellows here at the Byrd Polar and Climate Research Center back in the late 90s. And Jeff so fascinated me with his approach by being on the ground as a geomorphologist and a lake core guy, that I followed him to do a PhD when he became a professor at Syracuse. Unfortunately, he died way too young at 45. Don Rodbell, also part of the team, is pictured here, and you can see what we looked like back in 1997 around the landscape below the Kelkai ice cap where Lonnie was talking about. And our objective here was to think about how extensive was the ice even beyond the modern extent, even beyond the Coriolis, and to think about how rapidly those glaciers had changed over time. And one of the big insights that Jeff provided the community through his leadership was to get a longer core from beyond where the glacial moraines were in Lake Titicaca to give insight to the fact that maybe in the low latitude tropics, we had an earlier glacial maximum than the global glacial maximum. And he was able to do that with a grant that got a boat up onto Lake Titicaca that dwarfed anything in the Bolivian Navy. Don Rodbell's carried this forward even further and is able to get a core recently from Junin, which is another lake just beyond the glacial limits, up on the higher end of Peru, just above the city of Lima, where we have the separation of two mountain ranges in the beginning of the Altiplano. And these cores go back hundreds of thousands of years. So stay tuned to this space as these publications come forward. I had the privilege to be the supervisor for Nathan Stansel as a Byrd Fellow back in 2009. And he and I were able to think further about ways to look at changes in glacial extent by aspect, by going across the lateral gradient from the wet side to the dry side, if you will, and to think about the relative offsets of glacial extent that way. Now, in COVID, we've ended up right back to the field to continue with our work. But we do have a grant that's been funded that involves modeling with the atmosphere and the ocean to couple the flows of energy and mass to think about driving our glacier models and couple our understanding of the drivers with the evidence we see in the landscape. But in the process, we've also come across the need to develop a bigger database. Where were these individual glaciers? There's a whole lot of individual glaciers that respond quite differently because of the strong control of local topography on glacial extent. And so we had to think more critically about looking right down to the glacial valley perspective and quantify the extent of glacier changes at that watershed scale. So our locality specific glacial database has a lot of interesting data points. And I'm going to make a plea right now to the wider community that in these days, we need some collaboration. And we can benefit from a lot of the incredible skill sets that are developing here in data analysis and data analytics. We have big data here to think about. But our database was to then think of extending throughout the tropical Andes to develop moraines and dates, but also aspect and digital terrain information so that we could then anticipate using digital models of glaciers to fill those valleys and to test hypotheses. And Lonnie already mentioned cosmogenics. Cosmogenic nuclides that come and bombard the Earth system have given us a wonderful boon in chronology. Instead of just having to get radiocarbon material, we can now look at getting cosmogenic ages from the boulders on glacial moraines themselves. And you can see a bunch of students that we've taken into the field to help get samples of those erratics. My current master's student, Tal, is working on this project with us. And he is developing the skills to work with an open sourced glacier model. This is a wonderful innovation now in the in this new generation in their facility with lots of different skills. And so open source material is something that helps get the community involved. It also helps us give access to this material to our Peruvian colleagues. And what he's been doing with AUGM is the name of his model, the generic open source glacier model, is to think about specific areas in our Peruvian Andes and develop an inverse model approach. So growing glaciers to fit moraines in the past by dialing back the temperature and changing the precipitation. And some of the results have to be, glacier has to be calibrated against modern observations. So we use remote sensing imagery from satellites, but we also go back to the good old archives of aerial photography. And here's where I tip my hat to Henry Brecker, my good friend over here, who's taught me how to do the geodetic mass balance approach by getting stereo paired aerial photographs to get a volume change by getting a surface digital elevation model so that we can then look at the difference in total volume and mass of ice, which is much more revealing of energetic exchange than just the area change. And so when we look at these positions in the landscape where we've got some tentative dates, we can start to then get conditions of mass balance and precipitation, i.e. the two controlling variables of temperature and precip, to grow those glaciers. We can also take this model forward and think about how much time there's left before the glacier's gone and how much volume is in the ice that might feed into water resources below. Back in 2011, as part of the Mountain Research Initiative retreat to the Swiss Alps, I was privileged, again, to be able to go there, but to consider what the world's going to look like without glaciers. And this is a really complex question. And it's not simply one that we can address with just measuring volume changes. We got to think about the downstream effects of loosening up a lot of material. And as Lonnie rightfully put, what is happening with human civilization? What are people doing and how are they adapting to this environment? And so this has kind of been an overarching framework for another dimension of what we do. And really, as Ian set me up, I'm kind of the guy to try to think about humanizing and connecting these glacier water changes with the people. And I'm the worst guy to do it, okay? I'm a historian as an undergrad, so I like people, but I don't have the social science skills that it takes to really understand behavior. So we're trying to team up with other scientists in the social science. And this is my nod to social sciences and my colleagues across in geography to think about political ecology and things. Because as Lonnie alluded to, behavior is really mystifying. And at the end of the day, it's humans, and we're all not rational. So how do we respond to these changes? And change is very tricky to understand. But it's all that we need to do to think about it. So if you look at here at the Cordillera Blanca strung out across your panel, this is from the Pacific, this is from the airplane window, and you can see the Cordillera Negra in the rain shadow to the west of the Cordillera Blanca, and you can see in the dust-ridden valley of this Rio Santa that drains to the left here, which is to the north, and then out to the west through that steep canyon to the Pacific. And you get an appreciation for the controlling role of topography. But if you emplace society and its impact of glaciers and the melting of these glaciers onto this landscape, you start to realize the multiplicity of livelihoods that intersect here, from agropastoralism to mining. Peru's economy is held up by those pillars of industrial scale agriculture on the coast, irrigated by water from those highlands, and mineral export. Those have lots of ramifications, of course, for water quality as well as quantity. And if we're losing that water quantity, the quality issues become more emergent. But at the top of the watershed, there's still cultural importance. And as we lose these glaciers, these are the gods for local communities. So there's a lot of importance here that we need to be thinking about critically, because of course we're all implicated in this together. So we see kind of this critical conjuncture in a social hydrologic system between forces of globalization and climate change and its physical drivers and the loss of this frozen reservoir. So we've been trying to do within my group, we call ourselves the Transdisciplinary Andean Research Network, is to couple this perspective of climate change and hydrology with people. And this is a complex scenario. So connecting those glaciers to society involves thinking about water in its transformation. So what happens as it leaves that melting terminus of a glacier? Where does it go in the groundwater? How does it interact with stream flow? And then ultimately, what difference does it make to whom down below? So if we actually put some place names to that landscape view or that airplane view and take the A from our Tarn, Tarn of course is a glacial lake, so there's some significance to that abbreviation. You can see how what we've done in our research is go from literally the glacier down to the coast and tried to ask and examine a number of these questions and issues. And this is really, I only have 2 minutes left. So I'm going to give a quick snapshot of some of the things that we do in our group and end with a cautionary tale. We do lots of different things. And what's wonderful as a field scientist is being able to get students involved from lots of different disciplines in the same place at the same time, camping together and talking about our results. This has fueled a lot of interesting new experiments, like one good idea of a master's student. Why don't we take a thermal infrared camera and look at the edge effects around the melting ice to think about the energetics that's happening as the glaciers melt back and rock is exposed. So setting up weather stations with the help of Jim DeGrand on the ice and around the terminus, and then photographing every 15 minutes over a series of 10 days, we've been able to quantify long wave energy fluxes to the glacier that are added as the ice is receding. So these are feedbacks. With drones and even low-tech drones like kites that can fly for hours at a time with the valley wind systems in these glacial valleys, we've been able to map with very high resolution using structure for motion algorithms from the cameras dangled below, what that landscape looks like, and think about coupling that with hydrologic experiments and dye tracing to look at where in this landscape is stream water emerging from the groundwater and where is it leaving the stream to go into the groundwater. Getting into the thermal infrared through multispectral drones, we've been able to then think about mapping where those water resources are and how they're impacted by human activity like grazing. And this is Dr. Drone, my first PhD student who designed his own drone, who's now a postdoc in New Zealand, mapping the Tasman Glacier with the drone that he invented and built to fly at high altitude. This is just a little side note to note that Forrest has started a group with engineering students and geography students, a lot of undergrads involved in the lab downstairs, called the Mountain Drone Team, which is an exciting way to rally a lot of cool ideas and focused activity to think about these challenges of higher observations in resolution in these landscapes. Forrest's dissertation itself is also about compiling information at this interface from space down to the upper levels of these glaciers, where again, observations are very difficult to do on the ground. Climbing to Huascarán is very difficult, as Forrest now knows, having gone with Lonnie to help with those cores in 2019. But what Forrest is now developing is a really rich database of imagery of annual cloud-free images to then look at the changes in mass in 3 dimensions at the above what we call the free. So we've done a lot of compilation here. And again, this is big data and a growing database. Some of the results of what he's showing, again, are changes in ice mass. Of course, this is the area, and you can see acceleration in the loss of area, but you can also see some really interesting patterns related to interannual variability, because this system is touched tremendously by ENSO. As we go further down the watershed, we can look at a landscape like this, again, to remind us that we have mine relaves right at the river course of the Rio Santa. What's going on as we think about water flushing through the system? How much water really is there? As the glaciers are melting, there's an initial buffer of extra water, but not being able to rely on historical observations, we've had to go back and reinstall low-cost data loggers that we've been sort of calling sustainable tech. But I gotta say, it's really difficult to maintain when you can't go yourself back to the landscape. So we're learning humbly, okay, that we've got to start to think creatively about communicating better and sharing data. But there was a lot of historical observations that were put in place in the 50s that ran for 50 years on wind-up cartridges. They seem to last longer than these satellite-linked battery-operated loggers. So we got to think more sustainably about how we observe. And this gets to one of our other COVID activities. Emilio Mateo is a PhD student who's compiled a lot of our observations, not only of weather stations, but of the discharge stations, and has just published an open source paper to then share those data. And that's the other lesson I think we're trying to learn here, is that we've got to get data out there for people to use, especially when we can't be back in the field. And it's reminded us just how privileged we've been in the past to be able to do this in person. His dissertation thinks about the change of debris cover of glaciers, because as you go and look at debris cover, it actually insulates the tongues of ice, but provides important additional reservoirs as well as risks to society below. And some of his big data analysis is viewed here in horrible resolution. You can't see anything, but I just want to appreciate that we have a lot of data. 15-minute data over 12 years is a lot to think about. And there's some really fascinating patterns that I won't dwell on because that's his dissertation. Finally, Gabriel Zaballos Castellon, is thinking about changes in cushion plant wetlands across the entire Altiplano of Bolivia. And he's been able to leverage, again, the Google Earth engine, big data analysis, and field validation using drones, and unique partnerships with park staff. And in fact, what you see here in the photo on the left is a great moment last summer when he was the first one in our group to get permission to leave, to go back to his native Bolivia. But he took one of the drones and gave it to the park staff and taught them how to use it. And they're now collaborating to get data. My cautionary tale. When I started my dissertation, Fulbright in Peru, I was affiliated with the Institute of Geophysical Research in Peru. And the director gave me a news clipping referring to the fact that in 1962, there had been a massive avalanche off of Huascarán that was followed 8 years later by a more deadly one that buried the entire city of Yungay. And he questioned me because at that point, they weren't doing climate change research. He said, do you think anybody's going to listen to your science? And he was pointing out the fact that there was two PhD students from MIT that were also world-class climbers that had climbed Huascarán on the North Face in 1962 after the first landslide, came down, and in this article from 1962, you can see them trying to warn the local population that there was an even more precipitous rock hanging over the city that if it went, would induce an even larger mudslide, that it would endanger the city. And in fact, that's exactly what happened. I published this as a postscript in a paper. One of those researchers found it, and he's still alive, from Australia, reached out to me during COVID. And he told me how he had been so devastated that his entire career trajectory altered. He was keen to do science. He wanted to impact society. When people weren't listening to his message, it was a horrible mental health feedback. I don't know what to do with this, but I do think we need to share these stories and archive them. And he even shared as a climber some of the images that we were able to reconstruct, and we can see again the change in this landscape. There's value in recording our stories. There's an important message here that we can often get isolated in our privilege, away from where people are. And we need to start to realize that there are limits to the science. So we need to work on messaging, as Lonnie's put it, and getting the story out and sharing those stories. And I think archiving them is an important role. Okay, last word goes to John Mercer. So his big obsession, this is a story that a lot of us at the Byrd Center know. In 1978, he published an article in Nature where he was concerned about the mass of the West Antarctic ice sheet because it's grounded below sea level. And if it goes, which it had in his insight in the past, sea level would rise really fast. And his quote that is pointed here is one that we need to dwell on here. A disquieting thought, this deglaciation may be part of the price that must be paid in order to buy enough time for industrial civilization to make the changeover from fossil fuels to other sources of energy. But let me just finally just end by saying that science, at the end of the day, is a human endeavor, and relationships matter. And these are just some of the many characters and people that I value deeply, that I miss, and one that died of COVID. And so this is Freddie, and it was really devastating news, but that's been common to us all in this time. So this is not an easy time, but there's a hope for the future, and I'm really proud to be part of this institute, where I think we're really doing a lot to couple these dimensions and go forward. So these are some of the grad students in our group, and there's our URL. So thank you again.
Well, thanks a lot, Bryan.
Probably too long, right?
Well, while we change over, we could
Yeah.
do a quick question or two. Anybody has one? Yeah.
I noticed that you're doing stream gauging, you're looking at the glaciers themselves. Does anybody age dating groundwater in the region to see if, there's very old, tens of thousands of year old groundwater in areas where there aren't current glaciers, to kind of give a further, historic perspective on what that region is like?
We have a half-written proposal. You'd be welcome to join. That's exactly what we're doing. So the question was, is anybody dating the groundwater? And it's a tricky question because a lot of the groundwater that's accessed is a very flat, fast-flowing system of alluvial fans at the coast. There's actually more danger now of saltwater intrusion as they've overpumped them in Lima. But up in the intermontane cities, which if you think back to Lonnie's ice core record, these are now growing because there's actually more water, but also really because there's economic opportunity. And one of those places levels out in a city nearby modern glaciers, where we have an opportunity to think about doing exactly that, to think about just how long it's been to recharge. When we do our small-scale catchment-specific tracing experiments, we see at least 50% of the water, even in the dry season, is coming from groundwater. The question is, what's the residence time? What's the turnover, the flushing rate?
That's the same stuff. I know even in northeastern Indiana, northwestern Ohio, in that region of Lonnie Basin, some of the groundwater is over 40,000 years old. So you can see these patterns. I think that would really matter.
Yeah, great. Thanks.
Sorry, traffic notifications.
All right. Well, we're going to move from the little ice to the big ice, I guess. And I'm glad you ended, Bryan, with John Mercer's warning, because in the late 70s, realization that the Antarctic ice sheet, which seemed far away at the time, could impact all of our lives. We're still wrestling with that so many decades later. And one of the most innovative ways, and probably the most difficult possible ways to get at this problem, is to actually go to those places and take measurements. And our next speaker Dr. Terry Wilson, who's a professor emeritus from the School of Earth Sciences, is leading a large effort, now in its 15th year or so, is that something like that, to weigh the ice sheet using geophysical techniques. And massive amount of work this takes. And for her leadership in Antarctica, and realize Antarctica is the only continent owned by scientists. That's why it's so awesome. And there's the governing board of Antarctica is the Scientific Committee for Antarctic Research. And Dr. Wilson's played a key role in the leadership there, and she recently won an award for that, the International Coordination Award, which just illustrates how key she is for science progressing for geology, geosciences in Antarctica. So with that, take it away. Oh, fresh off the plane from New Zealand too.
Not very fun. Thanks, Ian. Hi, everybody, and also people online. Today, I'm going to be telling you about a novel approach to understanding Antarctic ice sheet change using geophysical and geodetic measurements. As Ian said, I have been leading this project through Byrd Center in Ohio State since the last International Polar Year in 2007. I lead it on behalf of I lead it on behalf of a very large team at Ohio State and many other universities, lots of graduate students, collaborators from overseas. And so I can't list them all, but I'd like to acknowledge the contributions of these large teams, as well as the technical, logistic, and funding support from mainly the U.S. National Science Foundation, but also other countries to make this large project happen. So to introduce you to the framing of the Antarctic study, I'm going to use a short NASA video that shows you some of the ways that the ice sheet, sea level, and the solid Earth motions actually interact with each other.
Across our planet, sea levels are on the rise. And while our changing climate is a huge driver, the movement of the land itself is also an important factor. Around 20,000 years ago, ice sheets covered large areas of our planet. In many places, the weight of these massive ice sheets pressed down on the planet's crust and the viscous mantle underneath. This weight caused the surrounding land to rise and the sea levels to fall relative to that rising land. Over time, these ice sheets began to retreat as part of Earth's natural cycle of glaciation and melt. And as a result, this land began to rebound. Land rose up, and previously uplifted land sank or subsided, causing the sea level to rise relative to the ground. This adjustment of the land in many previously glaciated regions continues to this day, particularly in areas like the east coast of the United States. Today, if we were to travel to a region like Greenland, where massive ice sheets are now retreating due to a changing climate, we could see the land readjusting in the same way to the lessening load. This also alters the shape of corresponding ocean basins, leading to additional subsidence along coastlines. We live on a dynamic planet that is constantly in motion, and understanding the many drivers of sea level rise is critical to anticipating and adapting to our ever-changing home.
So the science team, in order to study these phenomena in Antarctica, which of course has the largest ice sheet and reservoir of ice on the planet, focused on this process called glacial isostatic adjustment, which is the deformation or warping of the solid Earth as the weight or mass of the ice sheet changes as it grows and shrinks. So in this little diagram, you can see that as the ice sheet grows, the Earth's surface subsides underneath it. And as the ice sheet melts again, it rises back up. And I'd also like you to notice that at depth, those arrows indicate that the solid Earth actually flows away from the site of the loading and flows back as the ice sheet disappears. The rate at which the flow and the motions of the surface of the Earth move is a function of the mechanical properties of the solid Earth below. That is, how strong, rigid, or weak fluid that Earth is. So that's at the crux of the process. To study it, what the team did was to deploy a network of autonomous GPS and seismic instruments at remote sites across Antarctica. So in the photos on the lower left, you can see on the rock in the short distance, a little antenna. That's the GPS antenna. It's recording the GPS signals from the satellite constellation passing overhead. That signal is recorded and it's actually transmitted back to the US by the Iridium satellite network. So we get our data back in near real time and we can measure the motion of this rock with a precision of millimeters a year through time. The seismic sensors that you can see on the lower right, they actually record the arrival of waves that are generated from earthquakes at some point on the globe that travel through the interior of the earth to the sensor. So the basic of the measurements that we make. So this map shows our network and all the red dots and symbols are GPS and seismic instruments that we have deployed and have been operating, as I said, starting from 2007. It's really hard to get a scale for Antarctica. I have that scale bar 1000K on the bottom, but who knows how big that is. So I just superimpose our familiar map of the states of the US on top of the network. And you can see that the network extends from the tip of Florida to the shore of Lake Superior, from the Atlantic coast to the Rocky Mountains. So it's very large scale in spatial footprint, but the distance between the individual instruments is quite large. In general, 100 kilometers, often several hundred kilometers between it. So how do we design this? We wanted to cover different geologic provinces. So there's East Antarctica labeled there. That's the older, colder, geologically inactive sector of Antarctica versus West Antarctica, where the red denotes where the continent has been stretching, trying to break apart. There's active volcanism in that area. We also wanted to span different ice drainage basins. Those are the gray outlines on the map. These are areas where the glacial ice takes the ice, flows down to different sectors of the Southern Ocean and delivers it to the ocean. And of course, overall, we were controlled by the distribution of rock because all of our sites are actually attached, GPS sites are attached to bedrock. And typically those are in the form of these bedrock nunataks where the topography is high enough that rock sticks up above the surface of the ice sheet. So the black on the map shows you in exaggerated form where there's rock across the continent. Those are where our sites are located. No rock, no sites. So these sites are spatially distant from the permanent US Antarctic Program bases. Those are the solid gold stars. They're also far away from even the summer field camps that are set up for the purpose of scientists accessing the deep field. So one of our challenges is simply getting to these sites to install and maintain our instruments. So a day in the life, we start at a deep field camp. We use these small aircraft called Twin Otters that are equipped with skis. They have a total payload or cargo they can handle of only about 2,000 pounds. So we cram it with as much gear as the pilots will let us take. We fly often 3 or 4 hours one way to get to one of our remote sites. We manually have to shift all our gear to the site. We have to either install or repair the instruments in whatever frigid conditions that we find at that site. And then we have to fly all the way back. A lot of our time, and the photo at the bottom reflects waiting at camp for weather to be good enough to fly anywhere. That takes most of our time when we're in the field. So another major challenge, of course, is the environment of Antarctica, particularly the strong winds. So we commonly arrive at a site to find that it's been knocked over, perhaps destroyed. On the right-hand side, there used to be a large brass antenna attached to that cable. It was ripped off, blown away, never found again. In the center photo on the bottom, the high winds caused the batteries to overcharge and a static spark caused them to explode. There used to be a box housing those batteries that was simply blown apart. But through time, we learned to environmentally harden our instruments so that they have continuously operated most of the time with relatively few surprises upon arrival. And so we're accumulating a very long time series of measurements from our remote sites. So on to the science. I said we're going to weigh the Antarctic ice sheet. How do we do that? There's really two components that are important that we want to measure and discriminate from each other. One are the relatively short-term changes in ice and snow. So for example, in the winter, you can accumulate extra weight of snow. It'll cause the Earth to move downward and back up in the summer. So if you look at the scale on the right, if you added snow or ice to the scale at the bottom, the spring stretches, the dial turns. That's what we're measuring with our GPS. And the calibration, the stiffness of that spring, we can determine from the seismological measurements. And I'll come back to that in a second. So the analog here is our standard inner spring mattress. You sit on it, it immediately goes down, you get off, it immediately springs back to its original position. We call this elastic deformation. The second component is longer term ice mass change. A glacier or an ice sheet is gradually shrinking. And so that is motion that takes place through time. We call this behavior viscoelastic. It takes a certain amount of time for the material to go down under the added load and a certain amount of time for it to respond and return to its original position. So here's our analog, the memory foam mattress, right? Once again, how fast that process happens is a function of the viscosity, stiffness, viscosity of the material. And you're used to thinking of viscosity in terms of liquids like the water and honey in the lower left, but of course there's a spectrum in rocks, and solid rocks actually flow, but with very high viscosity at the temperatures and pressures we have in the interior of the Earth. So again, the GPS is going to allow us to measure the actual motion. The seismology is going to tell us about the viscosity that controls the rate of the motion. So what have we actually done? First, with the seismology, of course, we're scanning the deep Earth under the ice sheet using seismic waves. And it's quite analogous to medical imaging, where a CT scan can reveal the shape and size and positions of internal organs in a horizontal slice through the body, right? In the case of seismology, we have an earthquake at some point around the globe. It generates energy that propagate through the Earth as seismic waves. We have sensors at different locations that record the arrival and the time it took for that wave to go from its source to the instrument. And that travel time is controlled by the material properties of the layer in the Earth. So that's how we can map how viscous, how rigid the interior layers of the Earth are, how homogeneous they are by using this travel time. So here is an example of what we've actually found for Antarctica. So on the left, we're looking at a horizontal slice through the Earth at 100 kilometers depth underneath Antarctica. On the lower right, we're looking at a vertical slice down into the Earth from the surface to 800 kilometers depth that goes right across the continent from one side to the other. The red colors indicate relatively slow seismic wave speed. And that's telling you that that material is relatively warm and therefore relatively fluid, low viscosity material. The blue colors, on the other hand, are telling you that the wave speeds are relatively fast, that material is cold, and it's more rigid. So the first striking thing is that you can see East Antarctica is blue. It is old, rigid, cold material. West Antarctica, on the other hand, first of all, you can see the warmer colors. It's warmer, less rigid, less viscous material, but you can also see quite a lot of variability within West Antarctica. And in particular, you see along the west coast of West Antarctica, that strip of red, which is the lowest viscosity material that we map underneath Antarctica. So that area is particularly weak. What does that mean? Well, we have a standard model of the Earth. You can think of it as the onion layer model, which is if you take a radius from the center of the Earth to the surface, every radius will go through the same layers with the same properties as you move through them. This is not definitely what we have in Antarctica. We don't have this nice, beautiful avocado with core and layers out to the rind. Instead, we bought the wrong avocado. We got one that has rigid parts that are embedded in softer material around it. So if you can imagine quite easily, if you were to load or mash this avocado, the rigid bits are going to behave differently than the softer bits around them. This is the case in Antarctica, both between East and West Antarctica, but internally within both segments of the continent that we've been able to map with seismology. So for the GPS, of course, as I've mentioned, we're going to measure how the Earth is warping and the pattern of that using GPS. And I want to use this video that UNAVCO made to indicate what we are measuring. Whoops, I won't do it that way. There we go. All right. So I've already mentioned this isostatic adjustment. When a whole ice sheet grows and disappears, the ice displaces, and we can measure that with GPS. However, if we zoom in and look at a GPS put at a margin of the ice sheet, we see a seasonal signal. Ice and snow accumulates in winter, it melts away in summer. We're measuring that up and down seasonally through time in this time series. You notice there's a slope to that line. That's the long-term shrinking of the glacier and the uplift that is occurring in response to that. And in this case, we had a slower rate followed by a more rapid rate as ice disappeared faster. So overall then, we can use this to monitor how the ice is shrinking with time. And I'm just emphasizing the vertical motion. I'm going to show you a map like this, where we use vector arrows that indicate how fast the land is moving up in response to this ice shrinkage. I still see my screen, but this is not what's on my screen. Suggestion, technical wizards here. Oh, I see. All right, well, so.
Yeah.
I swear I didn't touch anything.
But this is what happens when you don't use it for a year and a half, you know?
That's right. Just a little COVID technical glitch here, which is what getting to the cool part about the GPS too. Okay, thank you. We're back. All right, so I want to show you what we measured in Antarctica. And so this diagram, these vector arrows combine both the vertical and the horizontal motion together. They show the three-dimensional motion at each site. All in this rendition, all the arrows are the same length, but the color tells you how fast they're moving. So the red colors are moving really quickly. The blue colors are actually only moving a few millimeters a year, much more slowly. And what this view emphasizes is the pattern of motion. And what I want to point out is that what we would expect is that we would get the most rapid motion where the thickest ice was located in the past and has disappeared. So I think about those as bullseyes in the upper right. That map reconstructs where the thickest ice was 20,000 years ago at the last glacial maximum. We'd expect rapid uplift there and motion radially outward and away from those points. And so those blue dots on the map of Antarctica show where that should be. We do not find that. We find a pattern quite different than that. We have a rapid rates of motion in West Antarctica, and where things should be moving away from those LGM ice load centers, they're moving towards it. So completely different than the models had predicted. So we're going to turn the continent around, and we're going to look in from the West Antarctic coast. And this time the vectors are on a log scale to show their relative velocities with their size as well as their colors. And so if you look in East Antarctica in the background, you can barely see those vectors anymore. They're only 1 to 5 millimeters a year of motion, very slow. And the rapid motion is in the Antarctic Peninsula and in coastal West Antarctica. And we do have a bullseye. It's just not where any of the models predicted it to be. It's in coastal West Antarctica near the Amundsen embayment. And these are very fast velocities here, really faster than have been measured anywhere else on Earth so far. So how do we make sense of this? So first of all, let's look at what the ice sheet modern ice mass balance change is doing. We've mainly learned that from satellite measurements. So I'm going to show you another NASA video. And what it's showing is the change in ice mass through time measured from a pair of gravity satellites that orbits over the Earth, continuously measuring the gravitational attraction over the same point. If the mass reduces, the gravitational attraction reduces. And so you can see from 2002 to 2020, we've been losing ice, and the map and the red color show where the massive ice loss has been taking place. And so you'll notice that the major area of ice loss is here in coastal West Antarctica. Remember that this is where the seismology told us the Earth is weakest, and this is where the GPS tells us that the uplift rates are fastest. So those things coincide. So I'm going to relate those two things again with yet another video here. This was made by the European Space Agency to illustrate the results of our study in this area of fast uplift. So this is showing ice loss in this area. And here's our GPS that are attached to bedrock. So we're going to use those to measure the uplift of these sites as the ice sheet is losing its mass. And what we know from seismology, and in this example from other gravity measurements from space, is that the Earth here is very weak. So it flows very quickly. We get major uplift there, and we get this incredible dome of uplift that is much higher and faster than we expected from any previous model. And I just want to note this statement on the slide: such rapid bedrock uplift can affect the stability of the ice sheet. And I'm going to tell you about that in just a second. So why does this matter? Well, these gravity measurements, the gravimetry that tells us about ice mass change through time, is an integrated measurement. Any mass, whether it's vegetation or groundwater or ice and snow or mass change within the Earth, those are all added together in the signal that the satellite actually measures. So in our case of deglaciation, the ice sheet is losing mass, but notice that that dense material in the mantle is flowing into that same area as the surface of the Earth rises up. So what the satellite measures is this integrated signal, loss from the ice, but gain from the solid Earth. And so to isolate that ice mass balance, what you saw on that beautiful graphic from NASA that looks so clear and straightforward, they've actually had to subtract, make an estimate and subtract the solid Earth mass change, which is related to glacial isostatic adjustment, to get their answer, right? They had to apply this correction. So if you take our study, so here was what a standard answer would be in this cartoon. On the left, that block represents gravity change, the total mass that the GRACE sensors detected. In the middle is an estimate of how much mantle change is related to this process. You subtract that off, you get ice mass change. What we found instead was that GIA was much greater than predicted, right? We had to subtract more of this mantle mass off, and that means that the ice mass loss was actually greater, right? We are underestimating ice mass loss if we don't get that solid Earth correction right. So we really have to nail those. One way to do it is through better measurements of the type that we are making. So I'm going to finish with one other important implication of our studies about ice sheets. And what we talked about before is that the weight of an ice sheet causes the solid Earth to move and warp in response. But what we are going to talk about is that the changing shape of the Earth, that warping, can actually change the way the ice sheet behaves. Now, the standard view on this is from the last century and a half is that, sure, isostasy happens, but it's very slow. It takes thousands of years. Therefore, it can't really have any influence on how the ice sheet behaves. Therefore, when we think about projections of future sea level, we don't really have to worry about this phenomenon. Instead, what we've shown from our seismic and GPS studies is that in Antarctica, it's happening very quickly. And so this is a cartoon, not to show that the glacial cycles are going faster or slower, but simply that the Earth is responding much more quickly than we thought. And that means that it can actually interact with the ice sheet and cause it to change its behavior. So how does that work? I'm going to show you in a couple of cartoons. So this is a vertical slice through the ice sheet where it meets the coast of West Antarctica. So we have the ice flowing to the ocean where it's losing mass into the ocean. And in these settings, the bedrock, which is brown, has this slope into the interior of the continent, this landward slope that sets up something that's called the marine ice sheet instability. Once retreat starts, you can get a runaway effect that it keeps moving down that slope and you lose more and more ice, right? So we're going to take this forward in time and add bedrock motion to it. So here's time 1. We're going to freeze that and go to time 2. So the ice sheet has thinned through climate and ocean forcings that are related to it. But what we have to worry about now is what's the Earth doing underneath that? And you can see, of course, it's rising up. We've taken that weight off the top. The slope underneath the ice sheet is moderating. It's getting shallower. And importantly, in West Antarctica and glaciers like the Thwaites glaciers, they get pinned by topography in the bedrock. And so as this rose up, it actually intersected the base of the floating ice, it grounded it again, and it pins it and stabilizes it. So the flattening slope, the pinning, the ocean falling at this point are all factors that can stabilize the ice sheet, and therefore we're not going to lose so much ice. We're not going to contribute as much to sea level. And I'll just show you one study that uses this model. And so I'm first going to show you this video. It's going to show the grounding line where the ice goes afloat through time as, whoops, do that again. Got to click the right thing here. Here we go. So the grounding line is retreating. This is climatic forcing. And so that's the maximum point to retreat. But then it starts coming out again. It starts re-advancing a few thousand years ago and reaches the orange position, which is the present day grounding line. So the proposition is that it went farther back and came out again. Why would that happen? Particularly, we're in a warming world, and that's what the cartoons show. So here's our original grounding line 14,000 years ago. Ice sheet retreats, we get a floating ice shelf here, but of course we've triggered isostatic uplift. And if that happens with enough magnitude and fast enough, we can reground that shelf on the pinning point and ice regrows, producing an effective re-advance to a new position, right? So this has just recently been realized. It's been stimulated by our studies that show how fast this process is going. And so the question is, how important is this, right? We can see from these observations and models that the ice sheet may be significantly influenced and stabilized by solid Earth motion beneath it if it's fast enough. And that will moderate contributions of the ice sheets to global sea level change. So the question that we're looking at in the project as we go forward, we're continuing to measure at the moment until they cut off our funding. We'll see how long that lasts. But what we're hoping to do is improve this understanding of how important the solid earth cryosphere interactions are. This isn't a Pollyanna story. We're not saying that the ice sheet is not going to retreat and contribute mass to the ocean. Of course it is, but it's potentially going to be modulated by these solid earth processes, and we really need to understand better how they work, how important they are to answer our crucial question that we all need to know, which is how much and how fast is sea level going to rise around the globe. Thank you.
Great, thanks a lot, Terry. We're running a little behind, but we have some questions, so why don't we sneak those in before a break? Paolo?
Yeah, thank you very much. Very interesting talk.
Thank you.
My question is related about the glacial ice structure adjustment. How far is this propagated outside Antarctica? Does the seafloor around Antarctica feel this, or even the islands around Antarctica, New Zealand, does feel somehow this fluctuation of the ice in Antarctica? And I'm interested in particular of orbital time scale.
Yeah. So the question is, what's the spatial footprint of these kinds of effects? And yes, certainly areas adjacent to the continent, to seafloor, et cetera, they are feeling these phenomena. They are going up and down. The exact spatial limits to other continents, there actually is some new work emerging saying that there is an impact of ice loss across the other side of the globe. There's a lot of press just recently about changing the shape of the Earth from this ice loss, and that's essentially the same kind of phenomenon that I'm talking about. So we don't understand that very well yet, but it's something that has come to light recently that we need to start thinking about. Yes.
One more quick question.
You address this indirectly, but I'll address one more question. Okay. Farthest Antarctica, you got subduction zone. You call the rift zone, I call Backyard Basin, and then you have what I call the Craton.
Yep.
So if there was no ice at all, no effect at all, you'd expect to see uplift along the convergent margin. You expect to see subsidence in the Backyard Basin and associated with natural upwelling, basin range, and then a more stable Craton. How do you remove those natural tectonic fluctuations from the effect the ice effect or the static uplift associated with ice?
Right. So the question is tectonics versus isostasy due to ice mass change. You touch on a subject dear to my heart. Tectonics is why I started using GPS in Antarctica. And our seismic data show us virtually no seismicity in Antarctica. We do not think that any of those structures are active, with the exception of the tip of the Antarctic Peninsula. And the pattern that we see doesn't mirror in any way what you'd expect by long linear structures like plate margin or a Backyard Basin rift, whatever you want to call it. The geometry of what we see is completely fixes the ice pattern, not the tectonic pattern. And finally, the rates that we're measuring are far greater. Mountains rise maybe 5 millimeters a year. Typically, if you go to the Southern Alps of New Zealand or the Alps in Europe, the rates that we're measuring are far greater than what you see from tectonic processes.
All right, thank you very much. All right, thanks a lot, Terry.